I'm John Ludden, and I'm currently a professor in Heriot-Watt University. I was until September of last year the chief executive of BGS, and I was part of the team that actually created the Lyell Centre in Heriot-Watt University, which is a joint collaboration between Heriot-Watt and the British Geological Survey. I'm going to speak to you about a really exciting project that we have in the northern part of Iceland. It's called the Krafla magma testbed. And about 10 years ago, the Icelandic energy company Landsvirkjun was drilling in that area, and they actually were expecting to drill it to about 4 kilometers into a magma body, which would be about 1,000 degrees centigrade. But what happened was that they intersected a magma body at about 2 kilometers, which was actually 900 degrees centigrade. It's a magma body that we call a rhyolite. And so what this project is all about is actually they entered this magma body by mistake. And so we now know that that magma is sitting there. It's been there, it's probably cooled a little bit, but not too much. And we're thinking, well, actually, what if we were to drill into that magma body, or as near as we can get to it, for scientific purposes? It's the only place on the planet where we think we can actually drill into a magma body and stabilize an experimental system in that through a drill hole system. So what are the scientific challenges of doing this? And why are we doing this? It's potentially quite an expensive operation. We think around, for the first phase, about $25 million. So why would you do this? 3 reasons. One of them is to investigate what we call near magma geothermal energy. So the energy that's right next to a magma body, which will be about 10 times higher than any other geothermal hole that exists. Therefore, you can actually move to producing large amounts of power, say 10 to 20 times more power out of these sorts of drill holes near magma. And we actually know that around the planet, not just in Iceland, but we know around the planet, say in East Africa, not far from Nairobi, there are probably similar magma systems. And the argument would be, well, actually, can you drill into those magma systems and get much more heat than we are at the moment and use that power to power industry in Africa, for example? The Icelandic example is convenient in that the infrastructure is there, we know the magma is there, and we know how to deal with the problem there much better than we would in Africa. The second objective, which is kind of the more esoteric one and potentially more exciting, is can you actually drill into the magma body itself? So not just to the edge of it, but actually inside the magma body, say by a few hundred meters, and then stabilize the drill hole. And that means you have to cool the drill as you go in. You have to find ways of keeping your measuring system active. And so can we actually measure the temperature and the physical properties of this magma inside you? Now, why would you do that? You do that because that would then make a step change in the way that we monitor volcanoes. So currently we look at volcanoes from outside of the volcano, looking inwards by geophysics largely, or satellites. But can we move it so that we can actually be very close to the magma, at which point, or actually in the magma, at which point you may be able to trace the movement of that magma, and you may even be able to freeze it, which is probably a long shot, a moonshot, but you may be able to freeze the magma and actually stop an eruption. That's a long time, it's a long way ahead in terms of our thought processes, but if you can do that, then you could potentially save a lot of lives. An example might be in the Vesuvius area of Italy, where you've heard of Vesuvius, you've heard of Naples. There are volcanic systems underneath that area, and in actual fact, the volume of magma is relatively small, even though it can be quite disruptive. So, can you actually tame a volcano such as the one that destroyed Pompeii? And that wouldn't be tomorrow morning, but it may be for decades to come. So we need to start investigating that. And the third activity that we think we can do there is it's the only place on the planet, as I said, where you can get close to about, say, 1,000 degrees at depth. So we think we can use it for testing the sorts of systems that may be used on Venus probe. So when you go to Venus, you're dealing with temperatures in excess of 600 degrees. So you want to be able to do in situ testing of some of those sorts of things. And we think maybe we can do them downhole in Krafla. So how much power can you get from geothermal energy? Well, currently geothermal energy worldwide represents less than 1% of the global energy budget. So it's small. Now, we think that the geothermal energy will expand and will need to expand as you move towards more renewable sources of energy. We believe there are two ways of doing it, or two principal ways. One of them is what we call low enthalpy or low temperature systems. And those are very similar to what you might find in disused coal workings in Glasgow, for example. So the BGS and Heriot Watt are working on a system in that area to try and understand what we would call district heating, or heat from ambient temperatures. And then there's getting as deep as you can, or as close as you can, or as hot as you can inside the earth. So we think this magma or near magma drilling allows that. The advantage of Krafla is that the magma body is at around 2.2 kilometers, so it's accessible. So a single geothermal drill hole would normally yield about 5 megawatts. We think that a geothermal hole that's near a magma system will yield about 50 megawatts, so about 10 times that. But it's not just one hole. You could have multiple holes, right? So you could ultimately be producing 200, 300, 400 megawatts of power. And Iceland, interestingly, the company that we work with in Iceland is called Landsvirkjun, which is the national energy company. And 80% of what they do at the moment is actually hydro energy, so hydropower. And they're very interested in shifting towards geothermal power and testing this magma frontier. And interestingly, actually, there is a proposal which is stalled at the moment, but a proposal to put an electric cable from Iceland into Europe, probably into northern Scotland, and to ship a couple of gigawatts of power from Iceland into Europe. And then if you can test the system, establish a way of using this near magma energy, and then you can find other areas on the planet where there is near magma energy. And that we know, for example, that the drilling companies in Africa have drilled near to magma without realizing it. So, you need to be able to find it and then use it. So, as I said previously, actually, one good example is to go into East Africa, where we got the mid-continental rift system, which with magma quite near to the surface. So that's one area, and potentially provide a large amount of power for driving Eastern African industry. Because at the moment in Africa as well, a lot of their industry is driven by coal or by oil and gas. So can we move that to a more renewable source? Then there are other areas. I mean, there's Indonesia, there's New Zealand have hydro systems, geothermal systems, and then there's Mexico. Mexico is an interesting one as well, because the magma, we think there is quite near to Mexico City, and we think that you could actually power some of Mexico City. So that's the power angle, or the energy angle of this project. I doubt that geothermal is ever going to produce a major part of the world's energy, but if we can get it up from, say, 1% to 5%, then we're starting to make a difference. And locally, it would be locally effective. So areas where you've got geothermal energy, it could be almost 100% of the power source. And that's the example in Iceland, where you've got essentially geothermal energy and you've got hydro energy in Iceland, and so much heat and so much energy that they then want to export it, or they want to use it for, or they might want to use it for other things. So what they do in Iceland is they bring in tertiary industries to Iceland. For example, would be the production of aluminium. Aluminium is a very power intensive industry. So they got lots of power from geothermal energy, so they can produce aluminium there. From a more sustainable perspective, if you've got lots of energy, lots of power, excess power, and then you've got hydrogen and carbon, which are in your magnetic system anyway, or in the atmosphere, can you actually recombine that to make some sort of natural methanol? Probably you can, right? And then there's a lot of tertiary industries around Iceland, for example, involving volcanic heat and agriculture and aquaculture. So, fish farms and such like, in very controlled environments. In the Icelandic example, the volcanoes are always dangerous if you get too close to them, right? But the actual fact that in Iceland, the volcanic systems are fairly tame, and we understand them. They're not what we call explosive volcanoes, as you would get in, say, in Japan. In Japan, Mount Fuji is a big explosive volcano, and when Mount Fuji blows, it can be quite destructive. So you would have to, if you're going to do this sort of experimentation that we're talking about with a magma, you have to choose a system that is relatively stable, that you know how it's going to behave. Nonetheless, before we can actually get to the point of drilling into this magma body, and this is what we're planning now, and we have funding from the Icelandic government and from the UK government, or from the Research Council on this. We're doing what we call a phase 0. So phase 0 is actually how feasible, it's a feasibility study of what we're trying to do. So we believe we can do it, but I think before any private sector or any research sector wants to invest a large amount of money, you need to say, well, we've checked these things. So what we're doing at the moment is developing a solid management plan. We're developing a risk assessment for what might happen if we lose the hole, and what sort of scenarios might exist, and you can model those, right? And they're all safe, but it'll be based on a typical risk assessment type approach. And then we're also looking at engineering in these very hot systems. So there are cements that exist that people have designed that can work in very hot systems. So when you produce a drill hole, you have to cement it. So you want to cement it in place. And then because it's also relatively hot, it's cold at the top and hot at the bottom, you want your pipes to be flexible, so that you have to design what we call flexible couplings for the various pipes. All of that's possible and doable, but you wouldn't go ahead and do this experiment until you've actually done the due diligence and said, well, actually we've done all the tests, we think this is achievable. At the end of it, and then you convince the people to put quite serious amounts of money, which let's say about 15 million pounds into the phase 1 of this thing. And they would want some degree of security that you've done the due diligence, but they would also be, if you fail with your objectives, you fail to get there, right? The funders will say, okay, we did everything we could. This is really high risk stuff, but it's high reward. And I think, we know we can get into the magma body because the company's been there, and that well is actually one of the wells that they produced from in 2012. But they were kind of surprised, well, they were actually surprised to get to the magma, into the magma, or close to the magma, because they thought it was deeper. So they managed to stabilize it. But this time we would have to we know where it is, we could plan a little bit more for that, sort of stabilizing the well. But that steam, that was producing at around 500 degrees steam. So it's what we call supercritical conditions, right? And the steam actually that's there is not really steam; it's actually particulate silica that's being produced, which is actually optical grade silica. So you can actually mine optical grade silica from these sorts of environments too. I suppose one of the questions you might have is where are our energy systems going to be in the future? What sort of energy will we be using? And in particular, globally and potentially in Scotland as well. So I think in the Lyell Centre, one of our main themes is the energy transition. So in particular, in association with the Institute for Geoenergy Engineering, and some of the work that the British Geological Survey was doing in the past. It's trying to refocus that work, which might have had an oil and gas theme, on a renewable energy theme. So how do we store energy? How do fluids move underground? What new sources of energy might exist underground? and such like. So it's this shift in focus towards using the subsurface to produce energy, but in a renewable way. There are several projects now across Scotland, or across the Middle Valley of Scotland, looking at used mine workings, where things are a little bit warmer than the surface. You know, they may be 30, 40 degrees down there. So can we actually use that heat for district heating? However, one has to think about storing the energy. You cannot have an intermittent supply of energy, so you've got to either have a base load, or you've got to have a very efficient storage system, which allows you to be sure that you don't have blackouts in high power demand periods. So I think the Lyell Center, and BGS, one of our main preoccupations is how do we use the underground to store energy and produce energy. And the Krafla project that I've been talking about is an extreme of that. I mean, it really is way out there in terms of using very high temperatures, but potentially groundbreaking, not being a pun, but potentially groundbreaking new technologies. And the addition to the Krafla project is that it also has this theme around how magmas behave, and can we actually predict and can we actually stop a magmatic eruption, which is really a moonshot if you can do that. So thanks very much for listening and watching this video. We're really excited about this project. So if you are excited about the project, please go to our website. Thanks once again.